Yes, now it starts recording.
Okay. So the point here, we are talking about a major difference between the humidification, dehumidification system and the single effect or the multi-effect or even the flash, is that here we do not have a carrier gas. A carrier gas is going to have a capacity of the amount of water vapor that it carries, which is determined by the saturation condition. That up to a certain condition, when the air is saturated or the humidity ratio, the relative humidity is 100%, it cannot take any further quantities of water. Here in these systems, we are having the vapor itself is moving from one place to the other, and that gives us a freedom from the issue of that limitation here. Vapor is moving, so you don't wait for a carrier gas to move it. How it will move? You create like a pressure difference. And you know in fluid mechanics that the fluid is moving from one place to the other because of a temperature difference. So create a lower pressure at one location, and then pressure is going to go in this direction. And this is how you are driving vapor to move, not only in a single effect evaporation, but for a multiple effect or multi-stage flash systems, so that you have an increasing trend of pressure reduction going from one stage or one effect to the other. We talked about the system. We made a description of the system, that it is made up of two components, an evaporator and a condenser. The evaporator have tubes, horizontal tube bundle of steam, where steam is passing inside. Steam is coming from a power plant or simply from a boiler that is going to condense inside the tubes, giving off its latent heat. The seawater is sprayed outside to make a thin film on the outside surface of the tubes. This thin film of the seawater is going to be heated to saturation temperature, and then part of it will evaporate, and the rest will be rejected as brine. It's collected at the brine pool at the bottom and then rejected as brine. Whereas the vapor will first pass by a mist eliminator to make sure that it does not have any droplets of seawater. And then it is going to leave, going to the condenser. And the condenser is a shell and tube heat exchanger. The tubes inside are having seawater, cold seawater, that is going to create a cold surface for the condensation to occur. And we collect the condensed vapor from the shell side as product, whereas the seawater inside the tube is going to be preheated to feed temperature. We don't need it all. Part of it will be thrown away back to the sea, and only the feed quantity which is needed is going to enter into the evaporator to be sprayed. Saleh, you have a question, go ahead.
Doctor, why we should ensure that no water droplet passes with vapor?
Because vapor is assumed, or it should be, pure vapor. The process of single effect evaporation is not only used for drinking, but it is used, drinking, you know that we can tolerate some salts in the water, but if it is needed for some other industrial applications, like in feed water heaters, or for pharmaceutical applications, you need the water to be super clean, super pure. This is one thing. The second thing is that the surface, this vapor is coming at high temperature. If it is carrying some salts or water droplets, salty water droplets, that it may damage the condenser. The condenser have tubes. Normally you prefer to make it out of copper or brass nickel sort of components or tubes, materials. These materials cannot withstand the seawater at elevated temperature. Water enters at seawater temperature, which is small value, but if the vapor comes on the shell side at high temperature, then it should be clean from salts, otherwise it will affect the performance of the unit, which means that the materials are going to be damaged because of the salts.
Doctor.
Yes.
Sorry, but the oxidization is increasing when the temperature is high?
Yes. The precipitation of salt, انفصال الملح عن liquid which is coming, is promoted at high temperature.
Okay.
So that was a description of the system. And as you see here, we have a couple of heat exchangers. One of them is the evaporator. The second is the condenser. After the description, after we described the system, we looked at the temperature distribution. In the condenser, there is sort of linear, almost linear temperature increase from T cooling water to T feed. This increase in temperature is occurring due to the admission of the vapor coming into the unit. And then the feed temperature enters, or the feed flow enters the evaporator at TF. First will be increased sensibly to the saturation temperature, and then evaporation is going to occur. And evaporation is occurring because we have another fluid inside the tubes at higher temperature that is condensing, which is the steam that's brought into the unit. The vapor temperature that will rise is going to be at a temperature lower than the brine temperature by the boiling point elevation, and this is due to the salt existence in the water. Salty water would boil at a higher temperature compared to the pure water because of the salts that are existing in. The difference between the vapor temperature in the evaporator and the vapor temperature in the condenser is due to losses that happens in the transmission lines in the tubes. Tubes are having friction. They are having like minor losses like bends or elbows or any kind of flow controlling device that results in a pressure difference, and that pressure difference results in a minor temperature difference. However, in our calculations, we just tend to neglect this difference between the vapor temperature here and the distillate temperature here. We talked about the mist eliminator as well. And we said that this is needed to make sure that the vapor who's going to the condenser is pure vapor. And after this, we started doing the analysis, which is the mathematical representation of this cycle by making an energy balance for the evaporator and energy balance for the condenser as well. So that was basically what we did last time. We ended talking about the energy balance. This is the mass balance, liquid mass balance, and balance of the salt. And then we talked about the energy balance. We had another file that I shared with you, and we've seen that step by step, the equations. Now, after doing that, you are able to identify the parameters that affect the performance. Look at the figure in front of you here. What we have at the left is PR. PR is the performance ratio. And to remind you, the definition of PR is basically the mass flow rate of the distillate divided by the mass flow rate of steam. And this is how we are going to identify or rate the performance of conventional desalination systems. There is a relation between the PR and the GOR. Yes, the GOR was basically m dot distillate into HFG vapor. This is divided by m dot steam into HFG of steam, which means that if we simply, this is some sort of a fixed ratio. The HFG is a weak function of temperature, does not change much with temperature. So this is like a ratio. So as if the GOR is the performance ratio multiplied by a ratio of the HFG of the vapor over HFG of steam. This is just for you to recognize the relation between them. Now, at this figure, when we are looking at the performance ratio versus the boiling temperature, and in these figures to make an analysis for the performance, basically we change one parameter and keep the other parameters fixed so that we can see the effect of this parameter. So here we kept the feed temperature constant, and we have changed the saturation temperature in the evaporator, and we have seen how the PR changes. First observation, how do you see the changes of the PR? Look at the y-axis. What is the lowest value? 0.97. What's the highest value? 0.9724. Is that significant?
No.
No, it's not. So changing the TB does not significantly change the PR. Now the point here is, but why it's decreasing?
Doctor,
Now,
here TB is the temperature of the vapor.
this is the temperature of saturation in the evaporator. The temperature of the vapor, to remind you, is the TB minus boiling point elevation. The boiling point elevation is the temperature change due to the existence of salt in the unit. So they are related. When we consider, remember that when we did the balance, we said basically the source of heat which is coming to the unit here, or the evaporation is occurring at a certain temperature, where basically it's the latent heat issue which is controlling the parameters here. If I'm looking at a TS diagram for vapor or whatever, what happens to the value of HFG with temperature? As the temperature increases, the value of HFG, what happens to it? Decreases. This is why there's a decrease here. The decrease is insignificant by looking at the values, but the value of a change of the HFG is also insignificant. It's a weak function of temperature. So what's happening here is that the decrease in the PR as the temperature increases, because as the temperature increases, there is a decrease in the HFG value. So what this is saying here is that changing the boiling temperature does not change if you alter or if you vary the seawater temperature. This is the seawater temperature. And whether the seawater is at 15, 20, 25, 30, then it does not affect the performance. And the reason for this is simple, because we said here that we are changing the boiling temperature, TB, but TF is constant. If TF is constant, then the changes across the condenser, the inlet is T cooling water, the exit is TF, and TF is not affected because we said that we are fixing everything and only changing TB. TB has nothing to do with what's happening here, as long as it does not affect this. So you're getting the point? That now they are separated because we said that we are going to fix TF and only change the value of TB. That's why changing the TB did not affect the performance of the condenser in the unit here. This is the condenser. What we changed only is the value in the evaporator. So we are taking this TF, whatever the value of TF, or we are increasing its temperature to TB, but the value of TF is constant. That's why changing the cooling water temperature did not make any change in this this value or in this TB.
Doctor?
Now,
I have some suspicious regarding the previous claim. If we increase the temperature, then the capacity of air to carry vapor will increase, right?
there's no air carrying here. Remember, I said at the beginning that there is a major difference between this and the HDH. In the HDH, we're dependent on air to carry the vapor. Here, there's no air in the system at all. The vapor is generated, and then the vapor itself is moving from one place to the other. And this is a major difference, and this difference has to be clear, that we are not having a carrier gas in the single effect evaporation, in the multi-effect evaporation, and in the multi-stage flash. There's no air. The air as a carrier gas was there only in the HDH system.
Okay.
Okay.
Doctor, can you remind me, please, TF is referred to?
TF is the feed temperature. This is where we are making use of the vapor
seawater.
which is coming here to increase the seawater from T cooling water to TF feed temperature. We take TF here to further heat it to TB, and after that, evaporation is going to occur.
I see.
Okay. Then, if TF is constant, practically speaking, how TB is going to increase? It is going to increase by increasing the steam temperature which is coming in here. Is that clear?
Yes.
Now,
Yes.
this is typically or a typical expression that shows how increasing the temperature would affect the specific heat transfer area. Maybe to look at this and try to convince you with whatever we're having here, I would probably put an equation here, the very well-known equation that you have taken in heat transfer, that Q is equal to U into the area into a delta T. Either the delta T could be a simple temperature difference or could be a log mean temperature difference. That's okay. It's a temperature difference anyway. And here, when we are talking about the change which is happening, as the boiling temperature increases, then the value of delta T increases. And as the boiling temperature increases, the overall heat transfer coefficient increases. So these two values are increasing. To keep the whole Q constant, what should happen to the area? It should drop. I'm looking at the constant value of Q or very small changes in Q, but as the temperature increases of the TB, the overall heat transfer coefficient, which is basically a function of temperature, it increases. And I'm increasing one of the temperatures here and the other is constant, so the value of delta T increasing. To keep this value constant, the area decreases, and this is what you see here. As the temperature increases, then the surface area decreases. And that's what I'm writing here. As the value of TB increases, the HFG decreases for constant MD, QC decreases a little bit so that less water will be needed. I'm talking about how the water is going, or the flow rate is going to affect the system here. So the dotted, the circular dots here is for 30 degrees centigrade. So this is the 30 degrees centigrade water temperature. And here, this is the 15 degrees centigrade water difference, water temperature, which means that I'm looking at how the conditions can change between summer and winter. This is the condition in summer, and this is the condition in winter here. I'm looking at the specific cooling water flow rate, which means that I'm looking at the condenser. And in the condenser, I need to heat the seawater from this temperature to a value of TF. I should keep the TF constant so that the performance of the unit does not change. So if I need to increase from 15 to TF, then the delta T is higher. Delta T is higher, then the area is smaller. But if I need to increase it from 30 to TF, then the delta T is smaller, so the area is bigger. So it's as simple as that. And this is the effect of the salinity. Whether the salinity is high or low, the changes on the the effect on the performance ratio again is non-significant. Look at the two digits, they are almost the same everywhere, 0.97, 0.97, which means that the salinity does not really have a significant effect on the PR. And this is because the value of the boiling point elevation is a small value. As you change the salinity from say 28,000 to 45,000, then the value of the boiling point elevation is something is going to be within a limit of 2 degrees centigrade only. Which means that this kind of change in the salinity is not affecting the PR. What is the problem with the salinity? The problem is we are afraid of the corrosion scaling to occur to the surface of the tubes. And this is why in all of these desalination systems, we have to have chemical additives in a process that we call as pre-treatment of the seawater. So the seawater, as it being admitted before it enters the evaporator, it has to have a pre-treatment so that we add chemicals into it to take care of the issue of salt precipitation أو ترسب الأملاح on the surface of the tubes. And this is a standard process for any desalination system that we have. We have pre-treatment because as long as we are using metal surfaces, then we have to make sure that our surfaces are protected. There is two ways to do cleaning for the surface. If I'm talking about the inside surface of the tubes, so there is a common cleaning process which occurs, it's called ball cleaning. In ball cleaning, what we do, if this is the tubes, we prepare soft balls that are at the size of the tubes, and we send these balls inside. There is pumps that are pumping the fluid in. So as the balls are moving, they are making friction with the surface, so they are cleaning the surface. And this is very common. And if you walk through in any desalination system like the multi-stage desalination flash units in Jubail, you can find these balls falling on the ground because they have lots of it and they are continuously using. So that's something that you do, cleaning for the tubes while it is operating. Whereas if you need to clean the outer side of the tubes, then you have to shut down the unit, take the tubes out, clean it, rub it, and then put it to service again. So as far as the internal part of the tubes, cleaning is easy by using bowls, and the bowls are carried by the water or the salty water wherever it goes. But the outside surface of the tubes, that's something that cannot be cleaned by bowl cleaning. So if you need to do cleaning for these units, you are talking about a major maintenance, and then you have to shut down the unit, take the tube bundle outside, clean it, and then put it to service again.
Doctor?
Yes, go ahead.
Regarding the graph, in the salinity, what does the ppm stand for?
ppm stands parts per million. It's
okay.
a sort of a way to measure the salt concentration in the water, in the seawater.
Okay, perfect.
We talked about this before in the introduction, saying that if the value of the ppm up to 1,000 or up to 10,000, we call it brackish water.
Yes. We call it what?
Brackish water. Brackish water, like the water of the wells, al-abar.
Okay.
Brackish water, and actually some of the water wells in Riyadh or Qasim or Al-Jo or the other city which is near to Riyadh. I just forgot the name. Anyway, in parts which are far from the sea, the water wells are basically having a salinity of about less than or equal to 10,000 ppm. So this is brackish water. But talking about water at salinity greater than that, then we are talking about seawater or salty water. The salinity of the Mediterranean, for example, is somewhere here, and the Atlantic Ocean. Salinity in the Red Sea is closer to 40,000. Here in Dhahran or at the Gulf, basically, it is somewhere in the order of 46 to 52,000 ppm. So we have a higher salinity here compared to most of the other places in the world.
Due to what, Doctor?
Actually, it is normally, or one of the reasons is that when you look at the Gulf, you'll find that it is basically closed, which means that from the north it is closed, and from the bottom there is a small inlet, which is Holmes area. So here it's not open to the sea. It's not like the other seas all open to each other. Look at, for example, the Mediterranean, and which is it's open. It's much bigger than the Gulf. Here the area is less, so the rate of evaporation is a little bit higher due to the high temperatures, and accordingly the concentration of salts increases here. Mediterranean is much bigger. The rate of evaporation is not affecting the body of water that much. That's why of the salinity.
Yes.
Whereas the Atlantic Ocean, the Pacific Oceans, the Indian Oceans, all of them are open to each other. They are all connected.
Yes.
Accordingly, the salinity there is not affected.
Okay.
What's called the Black Sea in Jordan, this is totally,
Yes.
and this has the highest salinity ever in the whole earth. So that's the way it goes then. Because water there is not fluid, it's just a body of water which is there.
Perfect. Thank you, Doctor.
I'll just talk quickly about the evaporators before we jump into a numerical example. Evaporator is a very important part of the process. This is where the seawater is converted into vapor, and vapor is basically our product. We take it, we condense it, and then we are having sweet water. The kind of evaporators or the type of evaporators has developed over the years. Started with submerged evaporators, and then we went into the idea of falling film evaporator. A submerged evaporator is going to simply be, which used to be common long ago, you have a pool of salty water at the bottom here, which is this. This is all a big container having salty water, this. And then you are putting a heat exchanger, you are immersing in the heat exchanger inside the unit here. So the heat exchanger is surrounded by salty water, and you are running steam inside. This was performing poorly. Why the performance is poor? Because basically steam has to increase the temperature of all this body of water until all of it reaches the saturation temperature, and then the vapor will start to rise. As the vapor rises, it passes by the mist eliminator, and then the vapor is going to condense over the tubes of the cold water. So this part on the top is the condenser. It results in the condensate being collected here as your product. It is simple. It's talking about a one compartment rather than two, but that was an issue because this one it requires a tremendous amount of heat because you have to heat the whole system first. And the second is that it is immersed in the salty water. So the issue of scaling becomes significant here to the outside surface of the tubes. But this is the sort of technology they started with. Now, this has been improved later by having the issue of falling film evaporator in such a way that only a thin film of the seawater will remain on the surface of the tubes, and the rest of the water is going to flow down. You are only keeping a thin film, like a boundary layer, on the surface of the tubes. And that effectively heats this quantity, and evaporation becomes easier to occur. So this kind of arrangement is better compared to the submerged evaporators. It could be horizontal, as you see it here, or it could be vertical. We prefer this. Why we do prefer this? This is related to your study of convection heat transfer. If I'm talking about a system like this, and I have a horizontal tube, a vertical tube, as you can see it here, and there is flow coming from the top, flow of the seawater coming from the top. The boundary layer will start to form here, and the boundary layer thickness increases with distance. So as you are moving down, the thickness of the boundary layer increases. As the thickness of the boundary layer increases, the local heat transfer coefficient decreases, so that it does not become effective in heat transfer from the steam inside to the water outside. Whereas if your tubes are horizontal in a bundle of tubes or a tube bank as you have studied in heat transfer, then seawater is falling here, tube surface is hot. It will form a boundary layer. The boundary layer thickness is going to increase as long as you are moving in this direction. And after that, separation will occur. There is another tube below here. As the flow falls in, it will form another boundary layer, which means that we are keeping the average thickness of the boundary layer too small. If you remember that in convection heat transfer part that you consider in heat transfer, if you are looking at the heat transfer coefficient versus the thickness of the boundary layer, the heat transfer coefficient comes from very high value and then decreases, which means that at the edge of the boundary layer, we have the maximum heat transfer coefficient, and then it decreases. So here it comes very high. When it starts to decrease, the tube ended, and you are going to start with another tube. So it will be too high. And then when it starts to decrease, you have another tube. I'm talking about a tube bundle. So that's why the standard in the industry is using the horizontal tube bundle. The reason is to keep the heat transfer coefficient as high as possible, and then you have better heat transfer in between the steam inside the tubes and the salty water which is sprayed outside. Inside the unit, the evaporator, it's not necessarily that you put a single tube bundle. You can have different tube bundles, which means that the whole compartment may have the same volume, but you can change the heat transfer area by putting a one bundle or two bundles or three bundles. In industry, they do that actually. So we're talking about here, this is a description of difference between a vertical and horizontal evaporators. They started lately to look at the plate and fin heat exchangers because the surface area is too high, and they said that we can make use of that for operation. The problem again is that if you have fin surfaces, eventually with time, corrosion can attack the surfaces and it becomes difficult to clean. So they are trying to either increase the pre-treatment by adding more chemicals into it, or trying to find ways that would make cleaning less likely to be needed by coating the surfaces with a special material. And the nanotechnology have played a significant role here, that you are trying to coat your materials, your pipes, with a nano size coating. The size is too small. It does not reduce the overall heat transfer coefficient in one hand. On the other hand, it's a very smooth surface so that the salt will not precipitate, but it will slide over the surface and leave. And accordingly, you have a longer life between two shutdowns of the units. And that improves what we call the plant factor, that the factory is going to operate more period of time producing and you don't have to shut it down. Actually, what's happening currently with the units is that they probably shut it down for cleaning or for maintenance once every 2 years. So that's something that you can compare that with the desalination systems that started in 1950s, where they used to operate the system for a couple of weeks and shut it down for a month for cleaning and then operate it again. So what a difference is that because of the improvement in the kind of anti-corrosion, anti-foaming, anti-fouling kind of agents that have been added. In the last decades, the surface treatments have increased a lot, improved a lot by having the nanotechnology, and that actually works as a positive addition to the operation of the system. Yes, go ahead.
Can you please summarize again why the horizontal is better than the vertical?
To put that in one word, I would tell you that for the horizontal tubes, the value of the heat transfer coefficient is high. Why high? Because it is maximum at the leading edge where the boundary layer thickness is 0. And then as the boundary layer thickness increases, the value of H decreases a little bit. But the thickness of the tubes is a few millimeters. So actually, there is no opportunity for the heat transfer coefficient to drop significantly as the thickness of the boundary layer increases. So the average heat transfer coefficient is high. This is not the same with vertical tubes, where the boundary layer forms and increases in thickness so that the value of H drops as you are moving down. And accordingly, the H value for the vertical tube is less compared to the average H for the horizontal tube. Did I answer your question?
Yeah. Do you mean the boundary of the water? I mean, of
Yes, the salty water forms
vapor,
a boundary layer over the surface, and
yeah,
the
but we have
thickness
two
increases.
boundaries.
Excuse me?
I mean, we have two boundary for velocity and boundary for the temperature, isn't it?
Yes, I'm talking about the temperature boundary layer.
Temperature.
In the temperature boundary layer, this is the distance from the temperature as it changes from the surface temperature of the tube to 99% of the bulk temperature of the fluid which is being flown in here. This actually is the one that has this kind of profile as at the leading edge of the boundary layer, the heat transfer coefficient is infinitely high, and then it decreases as you are moving in. The shorter the distance that it has to travel, the higher the average heat transfer coefficient.